heat capacity for n atoms modeled as quantum harmonic oscillators. What does this mean? So we have n atoms, and how many directions do we have in space? We all live in 3D space, unless you're Super Mario, right? Super Mario lives in 2D, but we live in 3D space, right? So the way we think of it is 3n oscillators, right? So every atom has 3 independent directions, and we assume they're independent. So in practice, we are thinking of an atom's direction x and atom's direction y are as independent as this atom from some other thing. Okay, so we are thinking of it as completely independent. So we have 3n independent oscillators. What are these oscillators doing? They are moving, right? They are moving with some frequency. So these oscillators are moving with some frequency, which we don't know a priori. And as I mentioned earlier, when I said that Einstein was wrong and Debye was correct, it all boils down to what are these frequencies. And we'll get to that probably by the end of today or Tuesday's class. Also, Tuesday's class is on Zoom. Okay, it won't be here in person. If you don't have any place from where you can attend the class on Zoom, just come here, bring your headphones, and attend the video here. Okay, so it will be the same thing. I will be writing on iPad and it will be just on Zoom. And so the thing we are going to, we will work with this in a very general setup. We will say that oscillator number 1 has frequency omega 1, oscillator number 2 has frequency omega 2, and similarly, oscillator number 3n has frequency 3n. So we are making it super general. Even the same atom could have different frequencies in different directions. And that makes sense. Maybe you have some gradient applied, something is going on, something funky is going on, right? It likes to move in a different way. So given a certain frequency, in classical mechanics, we modeled things, the potential energy as a function of x, something like this, right? Where was the frequency playing a role in classical mechanics? What is the equivalent of frequency here? For a classical spring, K, correct, absolutely correct, right? So where is the K here? What property of this does K correspond to? It's the curvature, right? So it's half kx squared. And she said K because Hooke's law tells you F is equal to kx, right? That is the thing that it comes from. So in classical mechanics, we had this. Here, the only difference that we will have now is quantization. Okay, so you will have some ground state. The ground state can be 0, or it could be half h cut omega, or it could be u naught, which is the binding energy of the crystal, some ground state. Then you have the first excited state. Then you have the second excited state. And you can plot wave functions on this, right? The ground state, you will have nodes in the wave function and things like that. And you can, I'm not going to deal with wave functions, so I'm not going to plot it, right? Okay, but there are Hermite polynomials which define the wave functions for quantum harmonic oscillators. We can do all that. All we care for is that given a certain frequency omega alpha, the energy eigenvalues of a quantum harmonic oscillator QHO E alpha is equal to u naught, which is some binding energy of the crystal, plus half plus n alpha multiplied by h cut omega alpha. Okay. So we don't know what is the value of omega alpha. We know there are 3n oscillators. They can take some different frequencies. We don't know what these frequencies are. But given a certain frequency, depending on which state that oscillator is in, so in classical one, in this one, you are just moving along this curve, right? And in this quantum one, you are also in a sense moving along the curve, but it leads to quantized energy values, right? So n alpha can be 0, 1, 2, 3, dot, 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 right? So this is the problem we are going to deal with. Given a frequency alpha, the energy of that oscillator, given a frequency omega alpha, the energy of that oscillator is E alpha. So n alpha is something we studied last time. It is called occupation number of oscillator with frequency omega alpha. And we also interchangeably call it as the number of phonons. So if same as number of phonons. And if you have never done phonons, this seems very, very strange. Like, what are you talking about? What is a phonon anyway? It is the quantization of lattice movement, right? And if n alpha is equal to 0, you say 0 phonons of frequency omega alpha. If n alpha is equal to 1, you say 1 phonon of frequency omega alpha. If n alpha is equal to infinity, you say infinitely many phonons of frequency alpha. But the energy goes higher, right? So and Boltzmann probability will always work if you're working with, so the probability that you get a lot of phonons is going to keep dying down, okay? So these phonons are bosons. They follow Bose-Einstein statistics. The occupation number can go from 0 to infinity. There is no limit. When we do electrons, it will be only 0 or 1. So phonons are examples of bosons. Who here has studied phonons before? Raise your hand. Rachel is making her mind. Anyone who can emphatically raise your hand? I want to ask a question, don't worry. Few people, okay. But they are kind of funky. And if you have never studied phonons before, which is most of you, then it feels very strange. All I want to say is your strangeness feeling is justified, and you should feel equally strange about electrons. I'm not going to try to explain phonons to you. I will just say that you haven't felt strange enough about electrons then. Because electrons denote the quantization of charge, and phonons denote the quantization of lattice movement. That's it coming out. So that's what it is. So what do we have now? We have different oscillators. We have oscillator number 1, we have oscillator number 2, we have oscillator number 3n, right? So n atoms, each in 3 directions. Each oscillator has some frequency omega 1, omega 2, omega 3n, okay? And given this frequency, this particular oscillator can exist in ground state, it can exist in excited state 1, it can exist in excited 2. Independently of this one, independently of omega 1, oscillator 1, omega 2 can do the same thing. It can also exist in ground state, excited state 1, excited state 2. And the formula looks the same, but the separation between the energy eigenvalues is completely different, right? Because that's how these things are. That's how the quantization works. So let's get going now. Let's write down the energy of a given microstate of this system. How will we get that? To get that, we will go to every oscillator going from alpha is equal to 1 to 3n, right? And we will see what is the energy of that oscillator. This is the energy of the total microstate, okay? And I'm going to do something which is going to piss some of you off like really, really badly. I'm going to call this as equation number 12. It's relative. And it's same in my notes. So. Okay, so that was equation number 12. This one I'm not going to call anything. So use equation 12 in above. What does equation 12? Equation 12 is the value of E alpha, right? So we put in the value of E alpha in this thing to get our E nu. So that will be going from alpha is equal to 1 to 3n. So every oscillator you're counting. And you put in the value of the energy, and we will assume U naught is equal to 0. It's just a relative scale. It's not going to, if you want to account that it is not 0, just keep it. It will just fall out in the end. It does not matter, okay? We assume U naught is equal to 0. Again, it's just a reference, okay? So assuming U naught is equal to 0, this becomes half plus n alpha multiplied by h cut omega alpha. And this we call equation 13. I won't skip equation numbers from here with a high probability. So E nu is now, we split the summation in two parts. It is summation alpha is equal to 1 to 3n n alpha h cut omega alpha plus half alpha is equal to 1 to 3n h cut omega alpha. Okay. We have E nu. Now we don't still have any thermal. So now we have to deal with the partition function to do anything. Now we have to take this E nu and calculate, we will work with canonical partition function. We have to calculate e to the power minus beta E nu, summing over all microstates. Today, we are going to use one of my favorite relations in math that no one mentioned in the first class, and I also forgot to mention, which is the sum of a geometric series. Anyone knows what is the sum of 1 plus x squared plus x cubed?
1 over 1 minus x.
If x is smaller than 1, and we are going to use that one in a, if x is more than 1, then it's not true. So, but we'll get there in just a moment. So what do we have now? We are going to write down our partition function q of beta nv. This is going to every microstate and summing e to the power minus beta nu. So let's first write down e to the power minus beta nu before we worry about things up front. E to the power minus beta e nu is e to the power minus beta alpha is equal to 1 to 3n n alpha plus half h cut omega. And I'm going to mark a star here because in red, because this is a subtle point which I'm going to do next. This is the value of the energy in one microstate. But I also want to sum over all microstates, right? And this is where always the subtlety comes in. When we were doing the classical harmonic oscillator, this is the point where we suddenly popped out a 6-dimensional integral when we had to really think about microstate. Here, looking at microstates will mean looking at the occupation number and how it goes from 0 to infinity. Okay? This is the definition of microstate here. You're going to every oscillator and you're seeing whether it's n alpha for 0, whether it was in ground state. That's physically, that's what is going to happen, right? Every oscillator, if you can describe, one microstate would be where all the oscillators are at their ground state, right? Other oscillator would be, other microstate where will be one oscillator is slightly up. So, you know, if you listen to music on some app or something, you have those beats that show up, right? Like suddenly there are rising bars and things like that. So that's how it's going to look like. But this is a subtle point. Think about this carefully. Okay, so this is my Q, beta, and V. Who is missing? Disha, this is your homework. You will take it at the end? Okay, good. So, cool. Now, it's slightly more complicated. N alpha is not the same for every oscillator, right? N alpha is a different number for every oscillator. So this is N alpha in quotes. It's actually messier because I have a bunch of N alphas, right? So I'm going to have N1 going from 0 to infinity, N2 going from 0 to infinity, and things like that, okay? So let's explicitly write this down. This is going to be N1 is equal to 0 to infinity, N2 is equal to 0 to, and Chandler works through this example until this point, and then he leaves everything as an exercise, which is terrible. And 3n going from 0 to infinity, e to the power minus beta, and now let's spell out the summation in the power of the exponent also. What is that going to be? When alpha is equal to 1, that is beta n1 plus half h cut omega multiplied by e to the power minus beta n2 plus half h cut omega dot dot dot. Okay? Yeah.
Are you looking at a specific omega, or did you just draw?
Oh, very good. You're paying attention. That's great. My bad. Apologies. Now it becomes omega 1, omega 2, right? If it's not the same omega. Okay, I can tell you the answer. Einstein was very lazy. Einstein said, let's just assume everything has the same omega. And what did he call it? Omega Einstein. That gives a heat capacity which dies down very quickly. Debye came and said, no, we have to use the theory of solids. And Debye's omega change as per we will look at the probability of omegas, and they have a particular relation. Okay, so it's very important that we account that omegas are different, otherwise we will have trouble. Good, thank you for spotting that. So, but now pay attention that this term is the only term that depends on n1, right? So this can be brought over here. This term is the only term that depends on n2. This can be brought over here, right? So it's a complicated summation, but it's actually a product of summations. And guess what? They're all the same summation. Just the index has changed. The only thing that has changed is the value of omega, right? So once you do that, you get n1 is equal to 0 to infinity e to the power minus beta n1 plus half h cut omega multiplied by n2 is equal to 0 to infinity e to, again making the same mistake, terrible. Some people don't learn from their mistakes. That's me. Okay. And if you look at all of these, you can simplify it one step further. You can take the minus beta h cut omega divided by 2 outside the summation. Okay. So this will become e to the power minus beta h cut omega 1 by 2 multiplied by n1 is equal to 0 to infinity e to the power minus beta n1 omega 1. Here you will have e to the power minus beta h cut omega 2 by 2 multiplied by summation n2 is equal to 0 to infinity e to the power minus beta n2 omega 2 dot dot dot. And you have 3n such things multiplied with each other. Notice this one. This is of the form when n1 is equal to 0, this is 1, right? E to the power 0 is 1. So this is of the form 1 plus x square till infinity with x is equal to e to the power minus beta h cut omega 1. Okay. This is equal to again 1 plus x square plus dot 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 with x is equal to e to the power minus beta h cut omega 2. And this series 1 plus x square is a convergent series if x is smaller than 1. And in this case, x is smaller than 1 because you have e to the power negative number. Beta is a real valued number. I've been reading a book by Kubo where he comfortably talks about beta being complex valued. That blew my mind away. And the reason he did that is because you saw that canonical ensemble is a Laplace transform of microcanonical ensemble. And anytime you do Laplace transforms, it's better to switch to complex variables. So temperature can actually be complex valued also. It might help you with the math, but our temperature is nice and real. So this series, I'm going to switch to the next page. We have a series that looks like S is equal to 1 plus x square. Noah said the sum of it. Does Noah know how to prove?
What?
The sum?
Oh, yeah.
Okay, fine.
So,
Tell me.
okay, so you multiply
Oh.
both sides by x, and then you subtract.
Yeah.
uh,
So,
yeah.
correct. So S is equal to 1 plus x square, right? Multiply both by x. And this one multiplied by x becomes xs. This one becomes x, put it over here. This one becomes x squared, put it over here. You subtract the top from the bottom.
That's equal to x.
You get s 1 minus x is equal to 1 because x and x cancel, x squared and x squared cancel. And it's like Hilbert's hotel, there are infinitely many terms, okay, everything cancels. So s is equal to 1 by 1 minus x, okay? So if we go to our last formula, which is now equation number 14, we get q is equal to e to the power minus beta h cut omega 1 by 2 divided by 1 minus e to the power minus beta h cut omega 1 multiplied by e to the power minus beta h cut omega 2 by 2 divided by 1 minus e to the power minus beta h cut omega 2 dot dot dot. Okay, so in other words, we can write down our partition function for n independent atoms with 3n independent quantum harmonic oscillators as product alpha is equal to 1 to 3n e to the power minus beta h cut omega alpha by 2 divided by 1 minus e to the power minus beta h cut omega alpha. This is our Q. This does not help us entirely. We are not done yet. We can simplify it slightly more. We can bring the numerator back to the denominator, right? So the numerator looks like 1. So this becomes Q is equal to summation alpha is equal to 1 to 3n, 1 divided by e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. Okay. I'm going to stop in like 5 minutes. I'll write down the final expression, and the Einstein and Debye thing we will do in next class. So Q on its own is useless, right? What we need is log of Q. That's kind of nice because Q here is a product. That's not surprising. Why is Q a product? Because each oscillator we assume to be independent, right? And that's the partition function. If things are independent, the partition function is a product, right? So that's what we have. So we take ln Q. Ln Q, ln of product will become sum of ln, right? Ln of A, B, C is ln A plus ln B plus ln C. So I will write down in the summation formula, this is going to be alpha is equal to 1 to 3n ln of 1 by e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. Okay. We can take the log of 1 over thing outside and put a minus sign. Okay. So this equation, which will now be equation number 15. This is equation number 15. Let's write it down as ln Q is equal to minus alpha is equal to 1 to 3n ln of e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. Again, something very subtle is going to come now. So I'm going to make a red star here. Okay, so you pay attention. It's not obvious what I'm going to do next. So far, the thing that is left is, what the hell is omega alpha? I don't know what is omega alpha, right? It's just shown as a number. It's like, well, oscillator number 1 has frequency omega 1, oscillator number 2 has frequency omega 2. For a real chemical, for a real matter, how do you measure the frequencies of how atoms are moving? If you're doing DFT, which Ami has done and you have done, correct? You can calculate the Hessian, you can calculate the double derivative of the potential energy landscape, and you can get this. In reality, you do neutron scattering or some sort of scattering experiment where you throw lights on it or some radiation on it and you see how do things react, right? That's the idea. So, and what these scattering experiments measure is something known as phonon density of states. Neutron scattering being the number 1 way of doing it. There is a big lab. Where is the biggest? It's not Argonne. Is it Argonne? Running scattering experiments and collecting data. So phonon density of states G of omega is number of oscillators with frequency in the interval omega to omega plus d omega. Okay, so it's a mathematical way of saying number of oscillators which have frequency around omega. Remember, we did things like this for the macrocanonical ensemble also, energy around E. Here's the question. How many oscillators do we have? 3n. So if there is G of omega 1 oscillators with frequency around omega 1, and if there is G of omega 2 oscillators with frequency around omega 2, if I want to sum up the total number of oscillators using this formula G of omega, how should I write it? What is the lowest value the frequency can take? Can the frequency be negative? Probably not. Very strange. 0 to infinity. G of omega, D of omega. Okay. And in fact, I made a mistake here. Technically speaking, G of omega multiplied by D omega is the number of oscillators, right? If you're really careful about. So if you sum all of this up, how much should this be? 3n. This is obvious or not obvious. You're not going to be anywhere in the middle. Either you will be like, why is he saying this again and again? I know, it's of course it makes sense. Or you'll be like, I have no idea what's going on. Okay. So this is true because total number of oscillators is 3n. Okay, let's call this as equation number 16. Now we are going to switch. So currently, if you look at this equation, it's sort of like looking at an oscillator basis, right? We are going to every oscillator and saying, could you please tell me about your partition function? And then I add it to the next oscillator, right? I'm doing it oscillator 1, oscillator 2, oscillator 3. So it's like I'm looking, if all of you were oscillators, which is a good approximation, you know. If you were oscillators, I would go to each of you and ask, Julio, what is your frequency? Noah, what is your frequency, right? That's one way of looking at it. Another way of looking at it is to forget that you're separate oscillators, just get readout on what is the frequency distribution you have, okay? Maybe Samyak has the same frequency as Tucker. And maybe Max had a lot of coffee and her frequency is like, okay? So I read out the frequency. So I switch from this oscillator basis, switch to a frequency basis, okay? Don't do the summation in the oscillator space, do it in the frequency space. In that case, and also I have been dealing with LNQ. Why? Because LNQ is the same as, well, let's not write it over here. So we are switching to frequency basis, and what we are interested in is beta A, right? Beta multiplied by the Helmholtz free energy, which is the same as minus ln cube. So as per the above equation, this is the same as alpha is equal to 1 to 3n ln of e to the power beta h cut omega alpha by 2 minus e to the power minus beta h cut omega alpha by 2. And now if I want to switch it into oscillation space, I will have a very similar equation, but now I will sum from 0 to infinity. Instead of looking at each oscillator having this partition function, I will look at number of oscillators which have that frequency and then multiply with the same thing. Okay, but this is also a subtle point, the switch. So there were a few subtle points today. The first one was thinking about occupation numbers and how they go and behaving like that. And then second one was this notion of phonon density of states. And the third one was switching from oscillator basis to frequency basis. Any questions about this? Okay.
How do we show that you can just turn that that summation into that integral?
Because I have defined d of if in the large n limit, if there are a lot of frequencies, it's okay. If you have 20 n's, then it's not going to work. In the thermodynamic limit, this is something we do all the time, right? This is how calculus integrals are defined. When you do limit as a sum, you have a curve and you do like this summation, this summation, this summation, right? And you change it into an integral. That's exactly what you have done here.
Okay, I think I get it.
Yeah.
It's like if you just got rid of the ln,
Yeah.
just replace it with 1.
Yeah.
You have the, okay.
Yeah, it's limit as a sum. It's like the fundamental theorem of calculus. So
Right.
in other words, yeah, beta A is 0 to infinity d omega g of omega ln of e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2.
Wait,
Note-
where'd the minus sign go?
Because I'm writing beta A and not minus beta A.
Oh.
And the other mistake I did here is this is not omega alpha. Omega alpha was needed in the oscillator picture, right? When I needed omega Rachel, I needed omega Amy and things like that, right? Omega Amy. But now I am looking at the value of omega. I'm not looking at oscillator by oscillator, right? So the integral itself takes care of how omega is changing, right? So there is no omega alpha now. Notice alpha disappeared. So in principle, this equation is the real deal. You could go, if you have some material, you synthesize some fancy quantum material, which is going to solve the energy crisis or something, and you want to calculate the thermodynamics of this material, you assume the atoms are quantum harmonic oscillator. It's not a bad assumption. And you can calculate beta A for this material at any temperature. That's phenomenal, right? If you can get the Helmholtz free energy at any temperature, you can get all sorts of properties. You can get heat capacity, thermal expansion coefficient, everything. You're done. You straight to Stockholm, you know. The problem is this G of omega that you have to get either through quantum DFT type calculations, you run first principles calculations, or through scattering experiments, right? And often people improve this. Density functional theory has things called pseudo potentials and things like that, and they need to be improved so that G of omega from experiment agrees with G of omega from density of states. Otherwise, it's not useful. So how will this G of omega look like? And this is the last thing I'm going to do today. You will have an axis where omega can go from 0 to infinity, and G of omega will, at omega goes to 0, G of omega always goes to 0. Why? Frequency going to 0, the number of atoms with 0 frequency is going to 0. Does that make sense? Why? You're nodding your head very vigorously. But I don't think this is due to ground state. This is really about frequency. This is not due to ground state. This is due to how, so small frequency means, what does frequency mean? Frequency means how quickly you're doing this, right? So small frequency means really long time scale of motion, right? So at some point, so it's like saying one atom, which is like oscillating at the age of the universe. That's not going to happen, right? You won't have atoms like that. So G of omega always goes to 0. And for experiments, it could have some complicated curve. I don't know, I just drew a curve, okay? It could have discontinuities. The discontinuities would tell you about phase transitions. It would tell you that the material is moving from one crystal structure to another crystal structure. So these discontinuities could tell you about phase transitions or something interesting going on in the material, right? And I don't know, this is some curve. And you can measure such curve from DFT or from experiments. In next class, what we are going to do, but for any curve, the integral of G of omega, d omega, should be equal to 3n. That's the only thing. So the curve has to go to 0 at infinity also. If it's not going to 0, your integral is probably going to diverge. So that's not going to work. So next time, we will see two models. The first model is Einstein model. Einstein says that G of omega is equal to delta of omega minus omega Einstein. It's 0 everywhere except one frequency. All atoms have the same frequency. And we will see that this gives a heat capacity. So we have the Helmholtz free energy, right? So from Helmholtz free energy, we get the entropy. From entropy, we get the heat capacity. So we can run through that. And this is not going to be too hard of an integral because it's a delta function. But when you have delta function multiplied by a function, you have to differentiate the function. It's kind of painful. I'm not going to do right now. So this was Einstein, and Einstein's heat capacity dies down super quickly because he's saying he's a bit too brutal. He's like, every atom has to move with only one high frequency. And turns out, no, there is a distribution of frequencies in atoms. And that distribution is better given by a curve like this, which is d by G of omega, which is proportional to some constant C naught omega square for omega less than omega d, some dBi frequency. And this is our Einstein frequency. And I'm not making any claims about which one is to the higher or lower. It's just two numbers, okay? So dBi says, no, atoms are going to move. It will go to 0 frequency as you go to 0, the density of the probability of having oscillators. But beyond a certain frequency mode, you're not going to get oscillators. Why does this make sense? In real crystals, you can't have crazy high frequency. That's not going to happen, right? So he introduces a cutoff and uses a quadratic form. And if you like solid mechanics, you can see this quadratic form is quite realistic for most things. So next time, what we are going to do is to take these two integrals and work through equation 17. The algebra for that will show up in your homework 3 after the midterm, after spring break. You will work through all of that. I will give you the main gist of it. I gotta go now. Okay, so Tuesday's class will be on Zoom. I will be in Lausanne, Switzerland.